We need to make it. If we don't have it, death comes in short order. Insulin resistance may seem like an odd focus to the listener. This is the single most common health problem worldwide. Let's just make it clear.
Dr. Ben Bikman, a professor, metabolic scientist, and best-selling author of Why We Get Sick.
I focus on a seemingly obscure condition called insulin resistance.
We dive deep into the science of insulin, discussing its role in belly fat, fat cell growth, GLP-1s, and even Alzheimer's disease. We don't want insulin in the blood for too long, but then it's also dependent on how much muscle mass you have. Is that correct?
Yes. One of the values of muscle, it is this great glucose consumer that it essentially tells insulin, I can't wait for you to come and knock on the door. I'm just going to open the doors myself.
There are people who are metabolically fit. They probably have a normal BMI who are opting for tirzepatide. I've never discussed on the podcast. I want to know what these drugs do in terms of insulin resistance.
Yeah, great. This is fun. You've unleashed me. So first and foremost,
Ben, welcome to the podcast. I've been eagerly awaiting this talk. I've read your book. I've been following you on social media for quite some time. I love tapping into some of the information you give regarding insulin resistance, metabolic health, and Alzheimer's disease. So we're going to touch on all of that. But I know that you have a very keen interest and you've devoted your entire career to studying insulin resistance. So why don't we actually just start there with first understanding what that is and why you think that is at the root cause of many chronic diseases.
Right. Yeah. Thanks again for inviting me. This is great. Yeah. Insulin resistance may seem like an odd focus to the listener. They may wonder why a scientist would devote his career to this. Just to put things in perspective, this is the single most common health problem worldwide. And it has over the years gone by various names, but people have, even if someone hasn't heard of or appreciates insulin resistance as a term, they've certainly heard of the metabolic syndrome. Just to help bring these ideas together, the metabolic syndrome used to be called the insulin resistance syndrome, which is in fact a more accurate name. It tells us where all of these problems are coming from. And so to your question, why does insulin resistance matter? It matters because of not only how common it is, which again is the most common health problem, estimated to affect about half of all adults worldwide. But then second is how relevant it is beyond the prevalence, which is that it is a common causal variable that virtually every chronic disease shares. Now, what do I mean by that? It's that we have this habit of looking at chronic diseases as being unrelated, totally separate, each having their own distinct causes and none having anything to do with the other. So an individual...
Well, that's why we have specialties in medicine, right?
Yeah, that's absolutely right. And specialties in medication, how we even will treat, like the particular medicine a patient may be taking. So I imagine an individual who every morning opens their cupboard and pulls out a medication or two for their blood pressure, a medication or two for their type 2 diabetes, a medication or two for their infertility, let's say, in men or women. Both of those are relevant. What I would hope to convey to them to varying degrees is that while these diseases do have individual or distinct causes, they also have one thing in common, which is insulin resistance. For these disorders and many, many more, insulin resistance is a common causal variable. And so much of my hope is that as we start to focus on the cause that is common and is arguably the most relevant contributor to these diseases, then we put ourselves in a position to, with some very simple, albeit sometimes challenging lifestyle interventions, we're really lowering the risk of pretty much every chronic disease.
So why are we getting it? Because I thought that at the root cause of almost every chronic disease was metabolic dysfunction. So there's a clear distinction between these two.
No. Metabolic dysfunction is a term that scientists coined many years ago, and it means whatever the scientist wants it to mean. It really does. Like it's one of those terms that doesn't have a clear definition. If I'm talking I could be invited to speak at a science conference, and the theme of the conference could be the origins and consequences of metabolic dysfunction. And the whole thing could be about nothing but insulin resistance, and it would check that box. At the same time, the whole meeting could be about oxidative stress and damaged mitochondria, and it would still fall under this metabolic dysfunction. So metabolic dysfunction is a term that is so broad as to have no meaning until an individual pins it down with some particular topic. I will pin it down and say, when I'm invoking the term metabolic dysfunction, which I sometimes do, although not too often because I don't like the lack of precision, what I'm saying is it's insulin resistance. But not many people would disagree with that when they appreciate that metabolic syndrome. Many people would say, well, that's metabolic dysfunction in its sort of clearest way. Well, that used to be called insulin resistance syndrome. And so metabolic dysfunction, I would contend, is another way, albeit a little sexier because it uses the word metabolism or metabolic, which everyone loves, of just saying insulin resistance.
Interesting. I find that I hear what you're saying, because I remember interviewing a doctor on metabolic dysfunction back in 2020. It was the first time that I really had looked into this and determined what it actually was, but you're attacking this from a whole different level. So, okay, so can we just discuss the pathology and pathway of insulin and just get a bit of a grasp on what it is, insulin spikes, glucose spikes, and get right into that?
Yeah, for sure. So let's just make it clear from the get-go that insulin is a necessary hormone. We need to make it. If we don't have it, death comes in short order. Once upon a time, type 1 diabetes was a death sentence. You have to have this hormone. What's important about insulin, to just put it in a friendly framework first, is that, yes, it's essential. Every single cell of the body will respond to insulin in some way. That is not common. Most hormones don't have a universal effect. Insulin is one of them, and that helps us appreciate just how relevant it is. Now, unfortunately, most people only think about insulin in its role as controlling blood sugar levels. That if blood sugar levels are going up, insulin will come up and essentially open the doors into certain cells to allow the blood sugar to go from the blood into the cell, and then thereby lowering blood sugar. Insulin, having done this most famous job, will then also retreat into the background, deciding that it's now time to take off work because the job is done. This is none of what I said is wrong. That is insulin's most famous effect, but it also sells insulin very short because it doesn't touch on the fact that insulin, for example, regulates energy use in neurons of the brain. Insulin regulates the production, the ability of cells to burn fat for fuel, and thus by regulating fat burning, insulin has a chokehold over ketone production. Insulin also affects, even beyond nutrients and energy, it has a direct effect on sex hormone production, which is why it's so relevant for the most common form of infertility in women, polycystic ovary syndrome, or what should aptly, more correctly be called metabolic infertility. So this just helps us appreciate the myriad roles that insulin plays in the body, from energy use to reproduction and many various roles in between.
So just so I'm with you, so insulin is a hormone secreted by the pancreas and we need it. That's all we know so far.
Yep.
It's a very good thing. If we don't have insulin as a hormone, we are essentially dying.
It's
That's
a
what
death
type
sentence.
1. Yes, it's a death sentence. Yes.
Yep.
Okay, great. That's where we are.
Yes, so that helps us appreciate the physiological role of insulin. However, as you alluded to in the question, there is a pathological role to insulin as well. Now, a disease-causing role to insulin. And that comes entirely, the poison is in the dose, where we now have too much of a necessary thing. A little bit of insulin works well and works to do everything we need. When we have too much insulin too often, that we now start to go from normal, healthy physiological effects into these pathological effects. So that now gets us into insulin resistance. And what's interesting about the high insulin is that this actually is both cause and consequence of insulin resistance. There are a handful of things that can cause insulin resistance in the body. I argue that the most relevant among these distinct causes is chronically elevated insulin itself. There are other causes, but for the sake of time, I'll just focus on that one. So the more often an individual is spiking their insulin, the more often the cells of the body will start to become resistant. So this is not, this isn't surprising. This is a fundamental biological feature that too much of a stimulus will result in a resistance to that same stimulus. So imagine the individual who is standing right next to the loudspeakers at a rock concert. If they stay there for too long, too consistently, too often, they will slowly start to go deaf. And then if they were talking then later to a friend at a normal decibel, they can't hear that friend anymore because they had become so deaf to the noise. This is very analogous to the cell that is inundated with insulin. Now, so chronically elevated insulin causes insulin resistance, where insulin isn't working as well as it used to. Those two things go hand in hand, where insulin isn't working very well and blood insulin levels are elevated. You cannot pull those two apart. They will always come together like two sides of a coin. Then it's tempting then to say, well, if elevated insulin is the problem, maybe elevated insulin isn't that common. To put things in perspective, if you look globally at the breakdown of calories per macronutrient at a global level, if you look at what percent of all calories are coming from carbohydrates or proteins or fats, over 70% of all calories consumed globally are coming from carbohydrates. Now, unfortunately, this is increasingly carbohydrates that come from bags and boxes with barcodes rather than whole fruits and vegetables. If it were the latter, it wouldn't be nearly the problem, because the next reason this is so relevant is that if you look at the insulin response to these same three macronutrients, carbohydrates, proteins, fats, when a human eats fat, there's no insulin secretion whatsoever.
Wait a second. So insulin is stored there, and then once we eat food, insulin evidently either rises to bring down glucose, which is the breakdown of different macronutrients.
Well, only carbohydrate though.
Only carbohydrates.
Yeah.
Yes.
So that's the thing that matters so much, is that we're eating 70+% of all calories are coming from carbs. That is doubly relevant when we consider the fact that fats don't increase insulin. If a human eats pure fat, if a human eats pure protein, there may be a modest increase in insulin in some people, although it's small. If someone eats pure carbohydrate, like pure glucose or pure starch, then there is a massive increase where insulin will go up 20 times and can take up to 5 hours before it comes back down. It can be even longer depending on how much carb the person eats. There was a human study to show that insulin, in response to 400 grams of carbohydrate, which is very easy to eat, insulin was elevated for up to 12 hours in young, healthy, college-aged males. And those are the kinds of kids who can take more metabolic abuse than anyone can take. And so if you imagine the 50-year-old man taking that same amount of carbohydrate because he eats 3 big bowls of cereal before he goes to bed, his insulin won't come down until he does that very same thing the next day.
Okay, so then we don't want insulin in the blood for too long, but then it's also dependent on how much muscle mass you have. Is that correct?
Oh,
yes.
For sure. Yes. Yeah. One of the values of muscle is that it is this great glucose consumer. The muscle is very hungry, especially as we get up and start moving it around. And so the more muscle a person has, the easier it is for them to bring down their blood sugar. So let's imagine we had 2 people with otherwise identical bodies, but one simply had more muscle mass than the other. If we were to give them both the same amount of glucose, of carbohydrate, we would see that the one with more muscle would be able to have the glucose come up and down. Not only would it not get as high, but it would get back to baseline much, much more quickly, because the muscle is so hungry that it's greedily pulling in that blood sugar. And one other note about the muscle is that when the muscle starts to exercise, if we actually get up and take a walk after we eat those carbs, we clear it even faster, because muscle has a way of pulling in blood sugar without the need for insulin to help. Normally, insulin needs to come to the muscle and knock on the door and then the door opens for the glucose to come in, thereby lowering blood sugar. But that would require insulin working well. Of course, an insulin-resistant muscle won't open those doors so readily, and the blood sugar will stay high. However, even in an insulin-resistant muscle in a person, if we start to contract and relax that muscle, the muscle gets so hungry that it essentially tells insulin, I can't wait for you to come and knock on the door. I'm just going to open the doors myself. So there's an internal mechanism within the muscle that will know that it's exercising, and it says, I need this energy now, so I'm just going to start pulling it in. So in that sense, it doesn't need insulin, so insulin can come down even faster. And indeed, during exercise, insulin does come down.
Yeah.
Insulin wants to store energy, whereas exercise is a state of breaking it down.
And so I experimented in 2020 when we're all in lockdown. I was wearing my very first CGM. And every time I ate something and I saw my spike, which wasn't actually that great. Only when I ate grapes, actually, it went really, really high. And so I would start to deploy these different protocols. I would do either star jumps, jumping jacks, squat jumps, or I would go outside for a run, and I would really look at the postprandial spike. And it would come down dramatically if I exercised. It would come down gradually if I didn't. But even now, if I put on a glucose monitor, I don't see it getting too drastic or out of hand. So is it true that the more metabolically stable or more metabolically fit you are, the less gradual the decline? So maybe the glucose spike will go up and it'll come back down pretty quick?
Yeah. So that is a sign of what we technically would call that as metabolic scientists. We say that's glucose tolerance, which is a very good kind of surrogate or very related to insulin sensitivity. So the more easily a body can consume glucose and get it into the blood than out of the blood, the more tolerant they are to glucose. They can handle glucose well. That's another way of saying insulin's working really well, because when glucose is coming up, insulin will sense this and say, if the glucose stays too high for too long, that's very harmful. I'm going to be the hero, come and knock on the doors of the cells, opening the doors for the glucose to go out of the blood into the cell to be stored or burned or a mix of both. And then insulin comes back down. Yeah. So the more readily a person can do that, which is one of the reasons I'm such an advocate of CGMs and the democratization to the access of them. I think the longer they're held behind these medical hurdles, the more we are depriving people of gaining their true insight into how their body handles energy and their metabolic flexibility and metabolic health, which is all just various ways of saying how insulin sensitive they are. But this is, again, you were able to see this, and part of the power of the CGM is that when a person can see how their body's responding, and including developing certain tricks and hacks to help them respond better, then the more they begin making their own self-imposed changes, rather than having someone like you or I pointing at them and nagging them as a coach, saying, you need to change this habit, and if you don't do it, you're responsible to me. No, when a person has a CGM, what they're seeing on their phone becomes the great motivator. That becomes their own internal voice saying, hey, remember what happened last time you did this? You didn't feel well. You didn't sleep well because you had a headache 2 hours later. And maybe that's a final comment I'll add. As people, one of the signs of glucose intolerance or insulin resistance is that as the glucose is coming up, there is an exaggerated release of insulin. Now, insulin isn't working perfectly because of the insulin resistance, so it still takes some time for the glucose to come back down. But when it does come down, it goes too far. And so the person finds that they have a period called a rebound hypoglycemia or low blood sugar after eating. The tragedy of this particular scenario is when the glucose starts to go lower than normal, it can stimulate hunger. And so the person who just ate more than they should have 2 or 3 hours ago suddenly starts to feel hungry again. Even though they just consumed 1,000 or 2,000 calories, there's no way they should be hungry again. And yet they're feeling hungry. It's because they went too high and then the rebound took them too low. And so the key kind of maxim to keep in mind in order to prevent that postprandial or rebound hunger with that hypoglycemia is to not go so high in the first place. So avoid the highs to prevent those lows and the hunger that comes with it.
And, that makes so much sense, obviously, with what we're eating and maybe adopting a more ketogenic lifestyle, if you will. But it brings a really good point around these so-called hacks, because when I was doing this, I was looking into, okay, what else could I do and I hate the word hack, so don't kill me. I hate it so much. It pained me. But I did read, and I was experimenting with this, I did read that Ceylon cinnamon, or just, cinnamon, having maybe a teaspoon of it can help bring down the glucose spikes.
Yes, that's right. Yeah, so there are some additional tricks. Like I imagine there could be some people listening to us.
Trick is a much better word.
Yeah, it's funny though. I actually also hate the word hack. It's become such a kind of bro culture term. I just can't stand it. So yeah, there are other little tricks small little interventions that are easy to do. If like imagine someone listening is wheelchair bound and has a hard time getting up and exercising, or wherever they live makes that difficult, or their schedule makes it difficult. By adding things like either cinnamon, cinnamon is a very good one. Ceylon cinnamon's the best. Water extracted. If there's a water extracted version of cinnamon, even better still from Ceylon, but that's one. And then another one is apple cider vinegar. Apple cider vinegar works surprisingly well, where you mix that in some water. I like to mix it in just a sparkling water, just a tablespoon or two of raw apple cider vinegar. And then there are a handful of other kind of spices that you can use that you can get, like berberine is extremely
It's the poor man's metformin.
Well. So these are easy things that a person can take.
And I actually took it. I've got to tell you, I took I took the Thorne metformin. When I had two, I got like a chronic headache, and I never get headaches. I don't know why that happened. That's the first time. And then I cut it back. So I just had the one. And then I learned that you should be having it and then fasting. So either having it first thing in the morning and maybe not eating till 11 a.m., depending on what time you wake up, or having it before you go to bed. I don't know if that's correct.
I'm sure. So was this metformin you were taking, like actual metformin?
No, I was taking berberine.
Berberine, okay.
Yeah.
I don't know. I've not heard anything with regards to the timing of it. Usually it's most effective when you're taking it with the thing you're eating that you know to be problematic.
Interesting. Okay, so this is the most exciting part for me. Now that we've gotten the education out of the way, I now want to link insulin resistance to various chronic diseases. And I'm first going to start with, of course, what I've devoted my life to, which is Alzheimer's disease. And where, right now, 55 million people worldwide have this disease. In my standpoint, and what I advocate for, is lifestyle interventions that you should be adopting to lower the risk of getting this disease. It's scary because this disease starts in our 20s and in our 30s. Then we get diagnosed in our late 60s, early 70s. So what role does insulin play, or insulin resistance, in this disease?
Right. I love that you've asked this question, in part because of my own work on the topic. My lab has published multiple papers now looking at these metabolic origins of Alzheimer's. If you'll allow me, let me just share a brief history of how this view has evolved. Until just very recently, and indeed in many circles it's still the case, Alzheimer's disease was viewed as a disorder of plaques accumulating in the brain. And these plaques would be just literally physically disrupting the connection along a neuron, where a neuron is sending its signals as rapidly as possible to help retain memory and proper cognitive function. So the view had been that it was entirely plaque-based. Now, there have been a large group of scientists, myself among them, who have said the plaques are simply a feature of some brains and not causing the problem, because we have had interventions, even in human trials, that have been drugs that very effectively remove plaques, and yet in no way improved cognition. And then this all really reached a peak about 3 years ago or so, when the original data that was used to begin the whole plaque-based theory of the disease was found to be falsified. It was fake data that had been put together by a scientific team that literally gave birth to the entire plaque-based view of the disorder. So it was built on a lie, and in my view, there has never been any convincing evidence to suggest that plaques are relevant at all. Thus, there's an opportunity for an alternate paradigm.
Which is probably why I don't know if you share this view, but you probably have it discussed in the current FDA-approved IV medications that are used to get rid of the plaque buildup in the brains, which is causing brain tissue loss and hemorrhages.
Yeah, it was. I bet we're referring to the same drug where the FDA approved a drug against the recommendation of the special panel.
Yes.
So a special panel had been put together to review this latest Alzheimer's drug and suggested, based on the evidence, that there was no benefit to the disease and it should not be approved. The FDA approved it anyway, and their justification for approving it was that they didn't want to discourage further development in the area. And so they approved a drug that they knew didn't work, that is horrifically expensive, and as you noted, has some meaningful consequences that are not good. So with all of this, hopefully crumbling of the plaque-based theory of Alzheimer's, there needs to be an alternate paradigm or view, and that, of course, has left a lot of room for the metabolic view to grow, and it is growing rapidly. As you noted, appropriately, it can start as early as people in their 20s. One of my friends and a person I respect tremendously as a scientist is a man out of a university in Canada called Sherbrooke University in Eastern Canada named Stephen Cunnane. Stephen Cunnane published a paper a number of years ago looking at young, healthy women in their 20s. Women do suffer from Alzheimer's disease more than men, and so that makes it very relevant. But in these women who had polycystic ovary syndrome, which is insulin resistance that's affected the ovaries, and in women who were matched with body weight and size and everything else and age who didn't have PCOS, he found that in the young women, remember, these are girls in their mid-20s, the young women with PCOS had a reduced ability in their brains to take in glucose. And now this sort of gets us to the heart of the matter. The brain is an energy hog. It has a tremendous demand for nutrients, and it primarily relies on only two: glucose and ketones. Now, they're not equal in their ability to get into the brain, and this is where some of Dr. Cunnane's work and work from my own lab has filled in some gaps, where glucose requires an insulin dependent mechanism to get in certain parts of the brain, including in the hypothalamus and some of these other regions of cognition and memory and learning. And so where you have glucose attempting to come into the brain to nourish it, because remember, the brain has a high energy need, insulin has to come and knock on those doors, like I said earlier about the muscle, to allow the glucose to come in. Ketone has no such regulation. If ketones are up in the blood, they can pass into the brain cells perfectly happily without any gatekeeper in telling them whether they can come in or not. The tragedy is, in a case of insulin resistance, one, it's twofold. One, not only can the brain not get the glucose very well because the insulin isn't working on knocking the doors open very well, so it's not getting its glucose well. And then and this is what Dr. Cunnane found, that in these young women with PCOS, their brain glucose uptake was significantly diminished. Now you would say, okay, that's fine, brain. Don't be so picky, just use the ketones. However, as I alluded to earlier, in a person who has insulin resistance and high insulin stops the production of ketones very, very well. Even a modest increase in insulin inhibits ketogenesis. It's a proper time for me to invoke this old poem, The Rime of the Ancient Mariner, where you have this dehydrated, dying, starving sailor dying of thirst, and he bemoans the fact that he's surrounded by water that he can't drink. This is akin to the brain being surrounded by glucose. Blood glucose levels could be higher than normal, and yet it can't get it. It's sort of crying out that there's glucose everywhere, but I can't use it. And so it's starving in the midst of plenty, crying out for ketones that the body is not making because the insulin is too high to allow it to do so. So Alzheimer's disease is insulin resistance of the brain. And then maybe my final point on the topic is that Dr. Cunnane and others, more and more groups now are showing this, my lab included, that when you do give the brain ketones, not only does it use the ketones very readily, Indeed, if the brain has a preference for any fuel, it is ketones far more than glucose.
Even if you aren't in a ketogenic state?
It depends on how the ketones get in. So we would say ketogenic if you're making your own ketones, or if a person is profoundly insulin resistant and has trouble getting into ketosis on their own, all the more reason to drink them. But however a person can raise their ketones, the brain starts using those ketones immediately. Even if a person has glucose levels that are this high, 6 millimolar, and they have ketones that are only at 2 millimolar, the brain is already shifting its metabolism to rely more on the ketones, even in a healthy person without insulin resistance. But it's all the more desperate when the ketones are the only fuel the brain can practically use.
And we want that, right? Because we want the brain to have its fuel source so it can then have the chance to fight off whatever it is it needs to fight off. I always talk about brain energetics and the fact that, we need to be able to fight, amyloid itself, the protein itself gets elevated when the innate immune system is activated. And that gets activated in response to an infection or stress, whatever that may be. So you want the brain to be actively fueled so you can fight off any type of inflammation that comes its way.
That's very well said. Absolutely. And then just with regards to strict energy use, neurons themselves need a constant supply of energy in order to maintain the normal nerve conductance. As it's sending a signal from point A to point B, it's using energy. In fact, not an insignificant amount to do that. If it can't use glucose to provide that energy in the form of ATP, then it needs ketones to do it. And this is where there are some exciting developments where you see that even in early stage Alzheimer's or mild cognitive impairment, if you give the individual ketones, their cognition improves. There are case reports that document Alzheimer's patients that are so cognitively impaired that they can't tie their shoes, they can't draw the face of a clock, of an analog clock at all. It's just absolute chaos. Give them ketones, and then a few hours later, repeat the assessments. All of a sudden, they can tie their shoes. Now, they can draw the face of a clock, not perfectly. They're still cognitively impaired, but there is absolute demonstrable improvement. And again, my lab's shown this, Dr. Ketone has shown this, and many others worldwide at this point.
My next question then is this beta hydroxybutyrate? Because I know there's different types of ketones, right?
There are generally two main ketones, acetoacetate and then beta hydroxybutyrate. Beta hydroxybutyrate is the main one that is circulating in the blood and thus the main one that is used. And so when it comes to various exogenous ketone products, they're all going to be based on BHB, whether it's a ketone salt, where it's beta hydroxybutyrate combined with a mineral, whether it's an ester, or whether it's these bioidentical BHB from like a company like Original Ketone. There are different varieties of them all.
And hopefully you get one that tastes good, because I got to tell you, I've been in the presence of a little small bottle. It's a liquid form of ketones, and it tasted like gasoline mixed with nail polish.
Well, let me please pardon this, because I'll just say my favorite, and I have no vested interest in this company. My favorite is the Original Ketone. It tastes like a fruit tart, like a tart fruit, like a nice kind of politely, sweetly sour taste. It is absolutely the best. Okay,
I love this. I love the thing, like the action items that we're putting against everything, because I would advocate everybody to adopt this, even without, we get so many questions and saying, but Louisa, I have the ApoE4 gene, or Louisa, I don't have the ApoE4 gene. I'm like, irrelevant, completely irrelevant. Everything raises your risk of getting this disease, and a lot of things can lower your risk. The ApoE4 gene should be redundant by now with the amount of research that we have on it. So I'm going to go out and get myself some BHP. Let's move on now, because I've got some exciting to me things that I want to talk to you about. Before I actually get into a paper, I'll first just touch on the now insulin resistance and obesity. I want to talk about fat cells, what hypertrophies them, what shrinks them, and the role that GLP-1. We've seen this rise of so many people now taking Ozempic and tirzepatide, and I want to know. I've never discussed on the podcast. I want to know what these drugs do in terms of insulin resistance.
Yeah, great. This is fun. You've unleashed me. So a lot of my view when it comes to insulin resistance and its chronic progression, There has been debate within the scientific field on this topic as to which tissue is the first one that becomes insulin resistant, which is the first domino to fall in the little stack that a child has put up, which is the first one that actually tips into the rest. Now, I would say the finger that tips the first one over is going to be the chronically elevated insulin. But even still, my finger tipping over the first domino is going to be the high insulin that we talked about earlier. But then still, one tissue needs to be the first one to really start suffering. And I very much embrace a fat first focus. It is the fat cells that become insulin resistant first. And it is all about how the fat cell grows. We commonly want to talk about fat as this just uniform, singular entity. And if you have more of it, you're insulin resistant and diabetic and hypertensive, etc. And if you have less of it, you're healthy. That is simply not true. If that were true, every woman would be more diabetic than every single man because women naturally have more fat than men as a consequence of her sex hormones. Women are naturally fatter than men, and yet they are metabolically bulletproof. A woman is a metabolic superhero, and that's all because it's not the mass of fat that matters most, it's the size of the fat cells. And because women have more fat cells than men do, as again a consequence of their sex hormones, women actually are healthier. Now, this then gets to the discussion where if you took two people, in fact, when I did my fellowship with Duke University in medical school in diabetes research, it was in Singapore, of all places, the beautiful Southeast Asian island state. And within Singapore, there was an interest in understanding why various ethnicities have greater or lower risks of developing type 2 diabetes and all of these metabolic problems that come with insulin resistance. And part of the problem was found to be the size of the fat cell and the different propensities that various ethnicities have to store that fat. So, case in point, let's imagine there were two versions of me. There is the white European version of me, typical kind of American mix that I am. And then there was, let's say, an East Asian version of me, both living in Singapore, exact same body size, but one of me is more Chinese, one of me is more European. And we add 10 kilograms of fat onto both of these versions of Ben. The Caucasian version of Ben is perfectly healthy. My metabolic health is unaffected. I just don't look as good in my Speedo. East Asian version of Ben, with my Chinese background, you put those same 10 kilograms of fat on me, I am profoundly hypertensive, I have type 2 diabetes, I have fatty liver disease, and I have erectile dysfunction. All of these consequences of insulin resistance and probably many more. That's because Caucasians have the ability to make new fat cells. That's a process called hyperplasia, relatively more than other ethnicities do. And when you're making new fat cells, your fat mass is going up, but the size of each cell is relatively modest. And it's size that matters most, as I'll mention in a moment. In the East Asian version, there's very limited capacity to make new fat cells. Indeed, it's essentially none once you get into adulthood. Thus, any fat gain is occurring strictly through a process called hypertrophy, where the cells themselves are getting much, much bigger. Indeed, a fat cell can grow to a level that no other cell of the body can, where it can easily get 10 or 20 times bigger than it used to be. But then here is the problem. It gets so big that it's almost like a water balloon that a naughty little child is filling up at the faucet in the kitchen. The balloon's getting bigger and bigger, and it's about to pop. You keep dripping the water in, and the balloon is going to burst. The fat cell is having its own version of this, where its membrane can only expand so much before it would literally fall apart. And so insulin is what tells the fat cell to get big. And so it must stop listening to insulin, and thus it becomes insulin resistant. But let me just highlight that point with total clarity. We have been spoon-fed an idea that all fat growth or shrinking is a matter of too many calories or too few or fewer calories.
Yes, calories in,
calories out. That is the dogma that we've beaten to death. And yet I can prove that wrong in my lab any day of the week. You can have fat cells growing in a little petri dish filled with calories, all kinds of calories, and they will stay very skinny and small fat cells until we do one thing, which is add a little insulin. You sprinkle on a little insulin into those cells, and all of a sudden it's like putting fertilizer on your lawn and your plants in your garden, and everything starts to grow faster.
Can I just stop you right there? Because I have so many questions. First of all, you should talk to Lane Norton. Second of all, is that the same as when you hear women who are menopausal or perimenopausal say, I'm doing everything I can, and I just don't seem to be able to lose weight? Is that the same for that way as well?
Yeah, well, in a way it is. In fact, women who start to go through menopause start to become, earlier I referred to a woman being a metabolic superhero until she goes through menopause, then she's immortal. Now she is as weak metabolically as her male counterpart is, he's always been like this, but with the loss of estradiol in particular, and even some progesterone and estradiol will help her body burn more belly fat while storing more on the gluteofemoral or the buttocks and hips, but also to make new fat cells when needed. That's why the woman has more fat cells than her male counterpart, but they're all smaller. So she has more fat, but smaller fat cells. But again, with menopause, with that transition, we have the loss of those sex hormones, and now she starts to store more fat on her belly. But at the same time of that happening in life, within the next 10 years or so, the number of fat cells that adults have starts to go down. Now that sounds like a good thing, but if the person continues to eat the same way they were before, then all of the remaining fat cells are getting bigger and bigger. Now, let me just say that as much as there is challenge to my idea, what I've been saying about insulin and fat cells, I can prove it definitively at the level of the cell. But someone would say, well, what about humans? We can do the same, that the lower the insulin level gets, the more and more impossible it becomes for the fat tissue to grow. And we see this in type 1 diabetes. A type 1 diabetic can eat 10,000 calories a day. And if they deliberately underdose, not even zero, but just deliberately underdose their insulin, they will be as skinny as they want. Their metabolic rate goes up substantially. They start to breathe and urinate out ketones, and ketones have calories in them as well. So whenever a person's in ketosis, the body begins to have to reconcile its inability to store energy, and thus it starts wasting it. And we see this happen in whole humans. In my lab, from human tissue, we found that when a person's in ketosis, their metabolic rate in their fat tissue is about 3 times higher than when they're not in ketosis. So all of this helps us appreciate that it is the size of the fat cell. And maybe one last comment before transitioning to GLP-1s. Once again, to the type 1 diabetic, a type 1 diabetic is given many pieces of advice, some of which is terrible when they're first diagnosed, some is good. One piece of good advice to the type 1 diabetic is to rotate your injection sites. They're told to never inject their insulin in the same place all the time. And that is because of what insulin does to fat cells. There are multiple papers published from labs in Japan looking at type 2 diabetic patients, type 1 or type 2, if they're taking insulin, and in people who did not rotate their injection sites, and you can see how much bigger the fat cells are in the cells that were getting the insulin injection compared to fat cells just a few centimeters away. In this, like you look on the belly, this spot here was getting the insulin injection, this spot here wasn't, and these fat cells are substantially bigger, so much bigger that it looks like the person has a tumor in their fat tissue bulging out of their belly, but it's just this oddly exaggerated fat growth because of all the insulin. So to look at the fat cell, in order for fat cell to grow, and this is sort of my conciliatory diplomatic way of accommodating these various perspectives. Some will say fat only grows through calories. It's the only thing that matters. My counter to that is, no, there must be some hormone signal, namely insulin, that tells the fat what to do with those calories, with that energy. And this is where it all comes together. In order for a fat cell to grow and fat mass to go up at all, you have to have 2 parts to this. One, you must have elevated insulin. The elevated insulin is what tells the fat cell that it's time to eat and store. The cell is not inherently rational. It doesn't know what to do with the energy. It's a naughty little child who doesn't know what to do with what it has. It needs to be told what to do. Insulin tells the fat cell it's time to grow. Now, having received that signal, the fat cell must have something to grow with. and thus the calories become relevant. But in the absence of even one of those, it becomes impossible. If a person has no insulin but high calories, it doesn't matter. That's the untreated type 1 diabetic that I talked about earlier. It's impossible to gain fat. In contrast, if a person had high insulin but insufficient calories, they would die, actually, from profound hypoglycemia, and no ketones, and the brain would starve and they would go unconscious or die shortly after if it wasn't corrected. So you cannot have one without the other. It doesn't work. If they're both elevated, now you are cooking with gas, as we may say, and the fat cells are going to grow very, very quickly. So all of this brings us to what are the best strategies to shrink the fat cell, because it's fat cell shrinking that improves insulin sensitivity. And that one brings some people to the GLP-1 drugs. Of course, dietary changes are the best way to do it. You want to control carbs in order to lower insulin, and then have some degree of fasting or some degree of restriction when you need to. You don't want to be eating all the time. Both of those are going to be helpful, and GLP-1 receptor agonists, as a new class of drug, relatively new, is a very effective way to do that pharmacologically, albeit with consequences that should be noted. As much as I do believe very firmly that it ought to be just dietary changes in the absence of drug, ideally, I acknowledge that in some people that is very, very hard, because in some instances we're dealing with very deep-seated dietary addictions that are not so easy. Because if I were to tell someone the simplest, best way to lower your insulin is to control carbs, the next words out of their mouth are going to be something like, I can't, or that's the one thing I struggle with the most. No one is sitting around on a Saturday night craving a plate of bacon and eggs. If only humans showed addictive or craving tendencies towards proteins and fats. We only show it. All of the neurobiology of food addiction has focused on carbs. That is one of the most consistent findings with food addictions. It's always carbs. Carbs alone or carbs with fat. Carbs is the common denominator here. So easier said than done. That is where I think GLP-1 medications can be helpful at the lowest possible effective dose, just to try to help a person learn to eat a little differently. But at the doses they're being used now, yes, you will lose weight, primarily because you just stop eating. You feel so nauseous because your intestines have slowed down so much that you have food that's sitting and festering in your stomach, which should have only been there for 4 or 5 hours, is there for 20 or 24 hours.
Oh my gosh.
And so you start to feel quite sick, and thus you don't eat. What we say, someone will say, I started taking the drug and my cravings went away. That's sort of a nice way of saying I started to really feel sick to my stomach. And so I didn't want to continue. In fact, people feel so sick that they get sick of feeling sick. In the US, 70%, in the UK, it's at 68% of patients who use these drugs at 2 years, 70% or 68% have gotten off the drug of their own volition.
And have they regained the weight?
Oh, yes. Oh, yes.
See, that's
it is the problem, especially because of what they lose. Just this week, there was a paper finding that GLP-1 shrinks heart muscle. There was already a paper published 2 years ago in the prestigious New England Journal of Medicine that found that up to 40% of weight loss is coming from fat-free mass.
Oh my gosh.
When a person regains weight, you think about it, if we're losing fat mass, for every 10 kilos, 6 kilos is coming from fat, 4 kilos is coming from fat-free mass. If 2 years in, I decide to get off the drug because I'm sick of feeling sick, 2 years later, I essentially have gained it all back. One of these comes back very quickly, and that's the fat mass. Imagine a middle-aged or older woman, her ability to regain any lost muscle and bone is essentially zero. Not totally zero, but it is going to be extraordinarily difficult for her to ever recover any loss of bone and muscle as she gets into her 60s or so. It is possible a little, but not entirely.
So the main mechanism of action of these GLP-1s is satiety. And because of satiety, you're not eating as much. You're probably in such a calorie deficit. Therefore, your muscles have nothing to feed off, so they waste away. Muscle is extremely energy consuming. It needs to be fed, really. You probably don't have that much energy, so you're not going to the gym. And most people most people are really not lifting as heavy to achieve a hypertrophy response. So we've got that. Okay, that's scary, and that's something that I hate. What is tirzepatide? Because I know that tirzepatide has both GLP-1 and GIP, but I still don't understand what these two do.
Yeah, tirzepatide is a joint medication with what you just said. So GLP-1, its primary action, well, historically, its primary action at the lower doses was actually to inhibit glucagon. And as much as we have focused on insulin's most famous effect is to lower blood glucose. Insulin has an opposite called glucagon, whose main effect is to increase blood glucose. In people with diabetes, type 1 and type 2, they have always chronically elevated levels of glucagon. And so at these low levels of GLP-1 inhibits glucagon. And by inhibiting glucagon, you were able to lower your blood sugar because the liver wasn't dumping out as much glucose, which is where glucagon is acting to increase blood glucose. So GLP-1 originally was used to just correct the hyperglycemia of diabetes. And then people were noticing that they were eating a little less, and then that became the target of how can we make it so they eat even less, and then the dose started going up to where it is now. So that's all of this is describing some of GLP-1's effect. And then the other one is gastric inhibitory peptide, or GIP. GIP is another hormone that acts to regulate blood glucose. So it's a little more specific, at least originally, to just kind of double down on the control of blood glucose. So there are so many versions, even currently, from these isolated molecule drugs such as Ozempic and Wegovy. Then you have tirzepatide, you have Mounjaro, other ones, exenatide, other ones that I can't even remember. But they're all going to be various versions or just play on the same theme of restricting eating and lowering blood glucose.
So I thought that there was also a fat depository component to GIP. Is that correct? Like, it also helps with satiety, but also helps in another way, making it like Ozempic on steroids, really.
GIP does have a central effect, just like GLP-1 does with satiety. It's more famous for being an insulin secretagogue, although that is debated. So what do I mean by that? An insulin secretagogue medication is a drug that will stimulate the beta cells of the pancreas to make more insulin. And GIP has been suggested that it will increase insulin, thereby helping control glucose. This has been shown to be the case in isolated cell cultures. In humans, it's less clear that actually is something that happens. But GIP has other, GIP, like GLP-1, it affects bone. GIP has been implicated in helping retain bone mass, which would certainly be good if a person's not eating much. But yeah, I mean, essentially it's one of these incretins where it's a gut-released hormone that controls metabolic processes.
I know that there are people who are metabolically fit. They probably have a normal BMI who are opting for tirzepatide at a very micro dose, which I believe I looked it up. I think, is it 2.5 micrograms? Well, whatever it is, 10 units, 2.5 micrograms or milligrams, whatever you want to call it. But that is this so-called maintenance dose. I don't know what it does. I don't know how it makes them feel. I don't know what the response is going to be if they already are healthy and metabolically fit. So do you have a problem with everybody now opting for this, even if they don't need it?
It's not as much. I worry about it. Yeah, so I have a little bit of a problem where people are healthy, lean already, and they are taking it because I worry that it's just an abuse of the drug's original intention, and the person who maybe has a bit of some body dysmorphia thinks they need to be even leaner than they are. I say that because I know some women who are on it, and I look at them and think, you have no business being on this drug. You're quite lean already. So I worry that it's being a little bit abused. But my view on the drug is it's probably the most effective way to help someone start to control their eating if they have addictive eating tendencies. And so what you're sort of suggesting is what I'd alluded to earlier, that my view on the drug is if the physician tells the overweight, insulin-resistant individual, you need to control your carbs. First and foremost, let's just do that. And they see each other a month later, and the physician asks, how did it go? I haven't done it. I did well for 24 hours. I just can't do it. I'm addicted to carbs. All right, let's try to break that addiction. Let's continue to focus on controlling carbs, being liberal with fat and protein, eat when you're hungry, don't eat when you're not. But here is the lowest. Let's try this really, really low dose of this drug, because one of its main effects is going to be to try to help you want to eat less. And maybe that will help you learn to control your cravings a little better, particularly for controlling carbs. And then my hope would be, with that lowest possible effective dose, the person's learning how to eat a little better. And then they're getting into such habits made easier by the drug that they can start to wean themselves off the drug over time. That would be, in my mind, the best possible version.
Yeah, we both share the exact same response for that. So thank you for that. So I want to move on now, and I want to talk to you about a paper that I have torn apart. And it's a 2016 study titled Hyperinsulinemia Precedes Insulin Resistance in People with Obesity. Now, this study and its findings align with many of the teachings that Peter Attia actually speaks about on metabolic health. But it demonstrates, so this study demonstrates that elevated insulin levels often occur before the onset of insulin resistance, suggesting that hyperinsulinemia might be a primary driver of metabolic dysfunction, not merely just a symptom. So I want to actually just talk about that study for a bit, because I've torn it apart. I've researched it. I don't know if you know about it.
Yeah, I do. This is, in fact, I have published, you could have cited work from the Bikman lab that show a similar theme. Yeah. In fact, I very much, this is something I'd alluded to earlier. There are a handful of distinct causes of obesity. There are three in particular that I focus on as primary, and this is a nice opportunity to mention them. Stress is a primary cause of insulin resistance. The more a person has elevated levels of the stress hormones, epinephrine, also known as adrenaline, and cortisol, the more they're going to become insulin resistant very quickly, too. But it's quickly resolved as well. A second primary cause, independent of any of the other three, or the other two, stress and the last one, is inflammation. When inflammation is dialed up in the body becomes insulin resistant very quickly. This is something that someone wearing a CGM can actually see and even use to predict the onset of a cold or flu. That when an individual has an increased inflammatory milieu within the body, they become insulin resistant very quickly. This has been something that you can track with autoimmune diseases, as has been published in people with rheumatoid arthritis, that when the disease is active, as autoimmune diseases can ebb and flow, as if the disease is active, the insulin resistance is demonstrably increased. As the disease subsides for a time, so too does the insulin resistance. Those are the two of the three. And then the other one is the one I've already mentioned, which is insulin. As much as elevated insulin is a feature of insulin resistance, it is a cause, but we're talking about obesity. There can be no increase in human obesity without at least frequent and often chronic increases in insulin levels. Insulin is an absolute necessary signal that tells the fat cells to store energy. Part of my problem with a lot of people who say insulin doesn't matter, it's all just calories in, calories out, is that they're often too ignorant or unaware, or in some instances perhaps just low intelligence, just stupid, to appreciate the clinical study intervention. That they will say, look at this group of people, they were all overweight, and they were put on either a low carb or a low insulin or low fat diet, and they all lost the same amount of weight. But that's because you're asking the wrong question. We shouldn't be saying, if we deprive, so the problem here is this huge confounding variable of, you take the average individual who's this chubby, eating a standard American diet, and put them onto a low-fat diet, guess what? They're eating less of everything, carbs included. And so it's no surprise that in every single study that has ever measured the patient's fasting insulin, on even a low-fat diet, guess what happens to insulin levels? It goes down. So as much as you say we just reduced calories, but you also reduced the total carbs coming in both groups, certainly even the low-fat group, compared to what they were eating before, and thus it's no surprise. So the question needs to be, which diet is most resistant to fat gain? A hypercaloric, low-carb diet or a hypercaloric, low-fat diet? That study has never been done at the level of a randomized controlled trial. There has been one case study published and found just what you would expect, that they found that in this person eating the exact same number of calories, albeit differing in fats versus carbs, when the person was on a low-carb version of the high-fat diet, they gained nothing. When they were on the high-carb version of the high-calorie diet, they gained a lot. And so we should be asking this question through the lens of which diet makes you fatter. And if it spikes insulin, you're getting fat. And there is decades of studies to show, including famous metabolic scientists like George Cahill. George Cahill, one of the most famous fasting metabolism scientists that has ever lived, was once asked, what is the difference between lean and obese people? He thought about the answer and replied, with all of his wisdom and experience, the obese person lives life at a constantly higher insulin level. And you see this again and again, whether it's fasted insulin or whether it is the insulin response to carbohydrate. A paper that I was just looking at, published in 1996 in the journal Gut, found that in obese and lean people, you give them the same amount of carbohydrate in the diet, and the insulin response goes up about twice as high and takes 2 to 3 hours longer to come back to zero, or to baseline rather. And this is why this is part of the problem. The more insulin is elevated, the more fat you're going to be storing, because that's what's telling the fat to store the energy.
So how does this then all tie into cardiovascular disease?
Oh, right. That is a good question. So there are myriad ways.
Just to finish up.
Yeah. Well, this is a doozy, but a relevant one, because as much as I painted the picture earlier that insulin resistance is the most common health disorder worldwide, the most common cause of death is heart disease. So heart disease is what most people with insulin resistance are dying from, and it's not a coincidence. It's directly causal. So just for the sake of time and clarity, I'll focus on one particular part of heart disease, namely hypertension. So high blood pressure is known to be the primary risk factor for heart disease. And most people would just think, well, I just have high blood pressure, not realizing that there is a strong metabolic component. There have been Dr. Gerald Reaven, another legendary metabolic scientist. He identified 5 distinct ways in which insulin resistance causes hypertension. And I won't mention all of them, but some of them include the inability of the blood vessels to dilate, as well as the blood vessels getting thicker and thicker and kind of growing in to themselves, narrowing the passage or the lumen of the blood vessel, making it be a much higher pressure. And with more pressure comes more damage to the blood vessel wall. But just to put this into perspective, if you have a patient who is taking an antihypertensive medication, so a medication to try to correct their blood pressure, and they adopt a low-carb diet, which is the fastest way to improve insulin resistance, usually their insulin resistance improves so quickly, which is seen by such a rapid improvement in their blood pressure, that within just days, and I'm talking 2 or 3 days, they often have to stop taking their blood pressure medications because their blood pressure is now going too low. That's how fast this happens. It's so quick that truly anyone listening, if you're on a blood pressure medication, you have to communicate with your physician's office, because you're going to have to start changing the dose almost immediately. That is how intimately causal insulin resistance is to high blood pressure. You remove the insulin resistance and all of a sudden the house of cards has tumbled.
Damn. So you really have, this entire episode has really changed my perspective on, well, first of all, now we've gotten the definitions of metabolic dysfunction versus insulin resistance. So you really have paved the way for educating the world on this one root cause, or one, if we can, trace all of these diseases back to a single point, in your opinion, and what your lab has shown is that insulin resistance is at the seed of that. And you've also written a book. What's the title of the book, and tell us a bit more about that?
Right. Well, it is strategically placed
I can
over
see
my
that.
shoulder. So the first book that really elaborates everything we've talked about most succinctly is my Why We Get Sick book. And I just present this paradigm that we've touched on, which is that as much as chronic diseases do have individual causes, they all have one thing in common, namely a metabolic origin in the form of insulin resistance. So that book primarily focuses on what insulin resistance is, where it comes from, and why it matters. But that just sort of describes the tree of disease, if you will. And then my next book, How Not to Get Sick, was basically the way of looking at this tree that we call insulin resistance with all of the branches that are the chronic diseases. Rather than pruning at the branches by taking various medications that only treat symptoms, this is a strategy to kind of cut the diseased tree down. So it's more focused on lifestyle interventions, kind of the what to do about it ending.
We love that. We love lifestyle interventions on the Neuro Experience podcast. Ben, thank you so much for coming on. I think we need to do a part 2 just dedicated to Alzheimer's disease. Now, knowing that you've done a lot of papers and research in this area, that would probably be a 3 to 4 hour episode. But I can't wait to get this out. And thank you so much for being part of the Neuro Experience podcast.
My pleasure. Thank you.